Greetings to all. Welcome back to the course on Introduction to Electric Vehicles. So in this video, we will be learning about how we can make a mathematical model of a vehicle using the equations we have lastly learned in the video. So to make a model or to make a mathematical model, we should know the basic equations for the system. In our case, the system is a electric vehicle or any vehicle for that case. So in case of the vehicle, the main equation relies with the what are the forces acting on it and what are the resistive forces acting on it. So the first force is the attractive force and the reaction or the relation of it with the resistive force and the balance between these two forces. So first here, because everything we will be talking about will be in rotational motion, we are not talking about a linear motion. So if we were talking about the linear motion, we'll be talking about the forces. But because the vehicle movement or the tire movement is a rotational movement, we'll be talking about the torque. So there are two type of torque. One is tractive torque, and the expression for it is tractive force into the radius of the wheel. And the second torque is our resistive torque, which is resistive force into radius of the wheel. This is a simple expression, so I'll be using this same expression for it. And when we are talking about the torque, then in terms of torque, the mass will be using J, we'll be using the term moment of inertia, and for speed in rotational term we'll be using omega. Omega is a rotational speed in radian per second. So the same expression which we were using, it is Ft minus F rotational is equal to mass, equivalent mass into dV by dt. This was the expression, same expression we are writing in a rotational form. Torque wheel means this is attractive force minus resistive force into J equivalent is a moment of inertia which the motor is experiencing. And this is a omega W, or this is a speed of the wheel, and d by dt. And this d omega by dt can be written as alpha. This is alpha is the rotational acceleration. So these are the all things we have written. So when we are making a model, we have to calculate what is the speed of the model. Suppose we are creating a black box. This is a mathematical model. So this black box, suppose this is a vehicle model or this is a hypothetical vehicle model. So there has to be one input and at least one output. So suppose input is the torque. Whenever the driver press the pedal, he is giving some torque command to the vehicle. So that torque command is, we say, is a reference torque command. And in response to that, the model has to generate some speed. The vehicle has to go at some speed. So that speed is known as the vehicle speed. So we have to design a model in which there is a input. That input has to be a torque, and there is a output which has to be a speed. So this is a rough idea how we are starting up the making of the model. So here we can see that speed is given here d by dt. So if I do some of the juggling up in this expression, we will end up with this expression. Okay, here the output is speed and input, I can use this torque as an input. Which torque? This tau w. Tau w is the wheel torque. Okay. So one thing which is important here, I have written in note that the dynamic torque or the dynamic torque demand of the vehicle depends on the equivalent inertia, which is the J equivalent, while the steady state performance or the steady state speed of the vehicle depends on the resistive torque. So in this expression there are two important things. One is J equivalent and another is T resistive. So these two are important thing, and these two will resist the force, or these two will resist the speed of the vehicle. When we are talking about J equivalent, it will be responsible for the transient responses. When we are talking about the resistive force, it will be responsible for the transient as well as the steady state also. Okay. Now the mathematical model. Now how to calculate the J equivalent? So J equivalent is calculated using the expression where m is the mass of the vehicle. M equivalent, why I have written this small e, is it is del into the mass of the vehicle. This del is a factor due to the rotational inertia. This factor is usually given for a particular vehicle. So m equivalent into radius of the vehicle upon the ratio or the gear ratio. G, the capital G represent the gear ratio. So this will give us the equivalent inertia. Now how to calculate the resistive torque? For resistive torque, we all know that the resistive torque is nothing but the F resistive into R of the wheel, radius of the wheel. And F resistive we have already known in the last video that it consists of three forces. First one is the aerodynamic drag, second one is the rolling resistance, and the third one is your gradient. So all these forces we have written here, 1, 2 and 3. These three forces are aerodynamic drag, the rolling resistance and the gradient. Okay, and this all three are being summed up and multiplied with the Rw, okay, the radius, and this term is your torque on the wheel. Okay, why we are multiplying Tm with the G? Because Tm is the torque generated by the motor, but when we are using a gear ratio, then the torque changes in ratio, the ratio of the gear we are using, it affects the ratio, it affects the torque at the wheel side or the actual torque which the vehicle is getting. To understand this, we can make here so this is a equivalent circuit, but so here we can make a box where the actual torque generated by the motor is this, and this is the gear ratio. So if the gear ratio is G, the torque on the wheel will be G into torque on the M. Okay, so this is one thing. And if the speed of the motor is Wm or the omega m, then the wheel speed will be by G. So this is a basic expression which we are using due to the gear ratio. If we assume that the gear ratio is 1, then there is no need for doing this. So this G comes from this very concept of using a gear ratio. Okay, so rest expression is already the similar one. So expression is like this: G m into G. This will represent our the attractive force. This Rw is the radius of the wheel, and these are the forces due to aerodynamic plus force due to rolling resistance plus force due to gradient. So these three forces added and multiplied with the Gw will give us the resistive forces, and this will be equivalent to J equivalent into omega of wheel and dt. Okay, this is the expression. So from here we can easily calculate this. Rw, and these are the all three forces. I am not writing the expression for the forces. Okay, this 1 by J equivalent, and this is the integration. Okay, so here we can calculate the speed of the vehicle in rotational terms. We can convert this into back to the longitudinal term or the latitude speed of the longitudinal speed of the vehicle. Okay, so this is the main expression which we are using. Now let's go to the model. So here we can see the model that we are using Tm multiplied by G. So here we are getting Tm into G. Okay, and here we are getting all these forces, the mg sin theta plus this aerodynamic drag, this is Fed, this is F grade, and this is F rolling resistance. We are adding these three and multiplying with Rw to get the actual value of the resistive forces or the resistive torque, and then we are subtracting the Tm minus all the resistive torque and multiplying with the 1 upon G equivalent. You can ignore this G for currently, and 1 upon J equivalent we are dividing. You can see here this is 1 upon J. I am doing this same thing in this expression in the MATLAB Simulink. So this 1 upon J equivalent we are doing, and then we are integrating. This is the integration. This 1 upon S is the integration, is in the S domain of the vehicle or the H domain in case of the MATLAB. So this is how I am obtaining this omega. This omega using Rw by G expression I am converting into the vehicle speed. This is the vehicle speed, and this vehicle speed is used by the aerodynamic drag. We all know that aerodynamic drag uses the vehicle speed in its expression. So this VV or the vehicle speed is being squared up. So here we are getting VV square because x square means we are squaring this particular term. Okay, so this is how we'll be doing the mathematical modeling of the vehicle. So in next video we'll be actually making this model in MATLAB Simulink, and we'll be simulating for some of the torque. So we'll be giving this is the input and here it is the output. Okay, so this is the input and the output. So we'll be giving some torque, and torque will be generating using some of the drive cycle. So we'll be using some any rural, highway or city driving cycle, and we'll be generating a torque, and depending on that we'll be generating the speed. Okay, so what are the drive cycle? So drive cycle are simple speed versus time data that is used for vehicle testing and certification. This is very simple. Drive cycle is nothing but a speed versus time data. Here you can see that there is a speed given, particular speed at particular time, and we have to test vehicles using this vehicle data or this drive cycle. So in India specifically, there is the Indian drive cycle, and it has 6 driving modes, each of 106 seconds, 108 seconds, and this is used for vehicle testing and certification in India. So drive cycle is nothing but a kind of test for the vehicle. Okay, so this Indian drive cycle was developed in 1885 by ARAI is the organization which is the known as the Automotive Research Association of India. So this is a organization which actually gives the testing and the certification to the vehicles, even e-vehicle or the IC engine vehicles. Okay, so this is all for this video. In the next video we'll be working on the MATLAB Simulink. Thank you.